Hi, we're going to talk about the idea of Kruskal's algorithm. So before we can talk about the actual algorithm, let's define some terms. So the most we've seen the term tree. So a little more formally, a tree is just a set of vertices that are connected to each other. The important thing about a tree that distinguishes it from a graph is that there's no cycle in a tree. Okay, so each of these lightly shaded ovals is a tree. A forest is just a bunch of trees. So all of these individual trees together, they form a forest. Now, two trees, we say that they are disjoint if they do not share any vertex and there is no edge that connect between um, any of their vertices. So any of these trees here, they are disjoint because, again, right, say this tree and this tree, they do not share any vertex and there's no edge between them. And finally, we say we can merge two disjoint trees if we use an edge to connect some vertex in each of them. So it doesn't matter which vertex we connect, but as long as we connect some vertex in the first tree and with another with some vertex in the second tree, we're merging them. And the result of merging is that we now have one bigger tree. So with that, we can talk about Kruskal's algorithm. Just, I want to point out that Kruskal's algorithm is one of the greedy algorithms. If you remember what a greedy algorithm is, it's if a company is run by a greedy algorithm, the company would try to maximize a quarterly profit rather than maximizing the total profit over, say, a decade. Okay, anyway, so this is a greedy algorithm that can work without doing any sort of backtracking. Okay, so now the overall idea is that we'll start with a lot of small little trees. As a matter of fact, we'll start with each vertex being its own tree. So that means, if we have 10 vertices, we'll have 10 trees. Each of this tree is just contains a single vertex. Okay, and then over time, we'll merge um, two of these trees by finding a safe edge that connects them. And we'll see what a safe edge is. So at every step of the way, we'll do this. So over time, we'll have bigger and bigger trees until finally we have just one tree left, and that would be our minimum spanning tree. So in a little more detail, this is the pseudocode. First step we do is that we initialize an empty forest. This forest will keep putting edges in it, and eventually this forest will contain all the edges that form the minimum spanning tree. The next step is that for each of the vertex in the graph, we'll create a tree that contains just that vertex. So that is this initialization step that we do here. All right, and then here comes what we do with the edges. How do we find the safe edges? So we sort all the edges by its weight. Okay, so and then we'll go through all the edges in the order that they're sorted, which is to say in increasing order or non-decreasing order. If each edge has two vertices, right? If those two vertices, if they are in two different trees, then we merge the two trees and then we add the edge to the forest here. Otherwise, we just throw away the edge and then move on to the next edge. So that's the algorithm. We'll explain why it works in a bit, but let's first see how it works by going through an example. So this is an example that I found in my trusted Introduction to Algorithm book. And so this is the graph, and we want to find the minimum spanning tree of this graph. So at the beginning, remember the first step is, well, we form an empty forest, and then each of these vertex is its own tree, right? Okay, so that would be the first step. And next, we're going to sort the edges by their weight. So when we actually start looping over the edges, the first edge we'll pick out is the one with the lowest weight, which in this graph is the edge with the weight of 1. So it's this edge here. Now we look at the vertices of this edge, which is H and G. Now remember, at the beginning, these vertices, each of them is in their own tree. So H and G is a tree on their own, and these three are obviously disjoint. So, so they are merged into the bigger tree, right, by this edge, and this edge is added to the forest. Okay, so the next edge we're going to pick out in the sorted increasing order would be an edge with weight 2. Now, there are 2 of them. It really doesn't matter which one we pick out. This algorithm will work. So let's say we pick this edge, and we look at the vertices of this edge, I and C. Well, they are in 2 disjoint trees, so we merge these 2 vertices into one big tree, one bigger tree here, and we take this edge and then we put it in the forest. Okay, so you can kind of imagine now the forest really kind of have 2 disjoint trees, right? These 2. Okay, going next, we will again look at the next edge in our sorted list, and that would be this edge. That is also the weight of 2. And again, we look at the vertices of this edge, which is G. Now G, if you remember previously, G is in this tree here. So we are looking at this tree and compare it against this tree, the tree that F is in. F is its own tree. So this tree with 2 nodes or 2 vertices, and this tree with 1 vertex, they are disjoint. So again, we can merge them into yet another bigger tree, and we put this edge into the forest. Okay, moving on to next. The next edge we're going to pick out is, we don't have an edge of weight 3. I guess we'll have to pick out an edge with weight 4. So let's pick out this one, and you notice there are actually 2 of them. So anyway, we picked this one out. A and B, they are in their own tree, and again, and they're disjoint. So they are merged into a bigger tree, and then that bigger tree with the edge itself, they're put into the forest. So now you can see in the forest, there's this 1 tree, 2 tree, and 3 trees, and they're all disjoint. All right, moving on, we have another edge that is of weight 4. So, and we look at the vertex that of this edge, C and F. If we go back to the previous one, C is in this tree, and F is in this tree. So these 2 trees are disjoint. So we will merge these 2 trees, and then we'll take this edge and put it into the forest with the tree, right? So now in the forest, there's 1 tree, and then there's a second tree, 2 disjoint trees. So moving on, the next edge we're going to pick out from our list of edge with increasing weight will be the one with weight 6. Now this one is slightly different because you look at its 2 vertices, the I and G, they are already in the same tree. So we do not need to merge them, and we do not add this edge to the forest. We just, this is not an edge that we need to use in the minimum spanning tree. Or another way to look at it is that if we add this edge to the forest, then we will actually form a cycle, which is as we know, a cycle should not be part of a minimum spanning tree. Okay, so the next edge after 6 is with 7. So 7 is connecting C to D, and C is in this tree that is part of the forest already, but D is its own tree. So these two trees are kind of disjoint, therefore we can merge them and then add this edge to the forest. All right, so we keep going, and I hope that you probably see, you should see what's going on here now by now. So the next edge we're going to look at is another edge with weight 7, but again, if we this edge would connect H and I, but if we connect H and I, then we'll form a cycle, or another way to look at it, H and I, they're already in the same tree, so we don't use this edge in the minimum spanning tree. Moving on, we should pick out the edge with weight 8, and this edge connects this subtree that A is in with this subtree that H is in. So these two subtrees, they're disjoint, so we will use this edge, we'll connect them, we'll merge these two trees, and we'll put this edge into the forest. And now you notice previously we have two disjoint trees in the forest, but now we only have one. Okay, and so we move on to the next step, and you can see the next edge is again another edge with weight 8, but again, if we use this edge, then we're either forming a cycle or we're trying to connect two vertices that are already in is part of the same tree. So we do not use this edge. We move on. The next edge is an edge with weight of 9, and 9 kind of connects this edge connects this tree with E, and so these two are two distinct trees, so we use that edge and we add that edge to the forest. And if we keep going, so edge with weight 10, well, this one, if we add it, we form a cycle, or E and F, they are already in the same tree, so we do not use this. The next edge would be 11, I guess. Sorry, 11. But again, if we use this edge, we'll form a cycle, or we'll just connect the same vertex that are already in the same tree. So we don't use this edge. And then are we done? No, we have one more. We have an edge of weight 14. But again, you can see that we do not use this edge as part of the minimum spanning tree. So as a matter of fact, well, at this point, we've gone through all the edges. And so we're done. And so this forest that is here, it has only a single tree with these thick edges. And this tree, you can kind of see it, that it actually spans all the vertices, and it is the minimum of such spanning trees. All right, so I hope by now you see how the algorithm works. So now I'm going to ask you to run the algorithm on this graph, which is from your readings, and find its minimum spanning tree. Okay, so I hope you've run the Kruskal's algorithm, and then the minimum spanning tree that you come up with should be one that looks like this, which again is given in the readings. Okay, so now that we know how the algorithm works, we want to know whether the algorithm gives the correct solution to the problem, right? That it actually finds the minimum spanning tree for a given graph. So what we have to prove is actually really the three things of a minimum spanning tree: that it's a tree and it's a connected tree, as a matter of fact, and that it's a spanning tree, that it actually spans all vertices, and then finally it's the smallest of such spanning tree. So we'll kind of talk about a proof here. It's not a mathematically rigorous proof, but I just want to kind of give you an intuition of why this algorithm works. So the first thing we want to prove is that the result, the output from the Kruskal's algorithm is a connected tree. So first thing is it must be a tree because as you see, every step of the way, if an edge would actually create a cycle, we throw that edge away. So we never add an edge that would create a cycle. So the result must be a tree. And then secondly, the tree is connected. And what connected means is that there's no vertex in the tree that is disconnected from all the other vertices in the tree. And the reason that it's connected is that, okay, so and this proof is kind of by induction. So the first step that we take is that each individual tree at the beginning, right, they come from, each of them contains a single vertex, right? So a tree with a single vertex is connected, right? Because there's only a single vertex. It's always connected to itself. So it's trivially connected. Now, and if we look at every step that we take, is that anytime we merge two disjoint trees, and the assumption is that those two disjoint trees, they are by themselves connected, and when we merge them with an edge, then the merged tree, the resulting tree, is guaranteed to be connected, which means we can get from any vertex in either of the tree to any other vertex in either of the tree, right? That should be obvious, right? Because if you look at the graph here, these two are disjoint trees, and when we use an edge to connect any of the vertex between them, then now we can go from any vertex from this tree to any vertex in that tree through this edge. So by induction, then this the fact that when we connect two disjoint trees, the bigger tree, when we connect two disjoint but connected trees into a bigger tree, then this bigger tree is itself connected. Therefore, by induction, this will hold until the algorithm terminates. So the resulting tree at the end of the algorithm is connected. So the next thing we want to prove is that this tree is a spanning tree, that it spans all vertices. And the reason for that is that we loop through all the edges, right, in the order of increasing weight or non-decreasing weight. And so we add the edge to the forest if the edge connects disjoint trees, right? So now, and remember, we apply this algorithm to a graph that is itself connected, which means then all of the original disjoint trees, right, at the beginning, each vertex is its own trees, which are all disjoint. So then because we go through all the edges, we will eventually add each of the vertices to the forest, right, by this process. And therefore, the resulting tree will span all the vertices. So the last thing we want to prove is that the resulting tree is the minimum of all the spanning trees. And in order to do that, we use induction again. And the way it goes is like this. So we have to prove first that at the beginning, the first spanning tree that we create is a minimum spanning tree. And the reason for that is fairly simple because, well, first at the beginning, we put all the vertices in their own trees, right? And then we pick out the minimum edge that connects two vertices, right? Because it's a minimum edge, so it's really between those two edges, sorry, between those two vertices, it's impossible to find another edge that has a smaller weight, right? So now we have our kind of a subgraph with the two vertices and an edge connecting them. So for this graph, that edge forms the minimum spanning tree, right? So that proves we picked the minimum spanning tree at our very first step. Now, what happens in the step n and then step n plus 1? So look at what we do at each step of the process. We find the minimum edge, right, that connects two disjoint trees. And because that's the minimum edge, there cannot be another one that can connect these same two disjoint trees but has a lower weight. So that would, and we merge the two disjoint trees. So that would mean the resulting tree is the minimum for the merged trees. Okay, so this is the meaning of induction, right? We prove every step that we maintain the result is a minimum spanning tree. So by induction, this says basically this would hold until the algorithm terminates. And therefore, the resulting tree is the minimum spanning tree for the whole graph.